All right, so the double slit experiment says this. So you have a piece of cardboard and you're firing particles at it. It could be electrons, photons, doesn't matter. We could think, actually, let's start off with you're tossing tennis balls at it. Okay, so you have one slit, and let's say it's big enough that your accuracy is good, and you throw a tennis ball through there. The tennis ball is going to hit on the other side of the wall, lined up with the slit, right? You throw more tennis balls, they're all going to line up right there, right? Okay. So now you have two slits, two openings. Now, if I throw at the left opening, I'm going to it's going to hit the wall behind the left opening. If I throw at the right opening, it's going to hit the wall behind the right opening, right? All right. All this, nothing crazy yet, right? Okay, makes some sense. So now we will switch to, instead of throwing a tennis ball, we're going to be shooting photons or electrons, doesn't matter. Light particles still matter, okay? A light particle is still a thing, okay? It's a super tiny thing, but it's still a thing. So we're throwing our photons, throw it through one slit, it shows up as a single thing. Now, you throw it through the other, you put the two slits, what you do is you throw it through there, and what you get is an interference pattern. Because what actually is happening is the photon's going through both slits. One photon, one tennis ball, goes through both slits magically. Okay. And what you end up with is this, so it actually goes through, instead of it traveling like a particle, it travels like a wave in that scenario. So even though tennis balls always traveled like particles, the photon traveled like a wave. When you were throwing it, didn't matter if you fired at the left slit or the right slit, it went through both slits. Well, that's a little bit creepy, but that's not even the creepy part yet. Just a little bit creepy. Like, okay, it's matter, it should kind of behave the same. So now you get this this pattern where instead of it, there being a little light dot through whatever slit, or even two light dots, like you think, okay, well, if it's going through both, you get two. No, you get a whole bunch of them, because it's this wave pattern, and you're getting like the pits and the peaks and valleys of where the light's hitting. Okay. We can kind of just accept that, like, okay, well, so photons are weird. They're these subatomic particles, and so they operate as a particle with one slit. They operate as a wave with two slits, and somehow magically go through the two slits. But this is where it gets creepy. We're only going to change one thing. We're going to look at which slit it goes through. Hands tied behind your back. Just look at it, or put a measurement device on it, something like that. Observe which slit it's going through. Now it acts like a particle again. It's just fascinating. The only thing that changed is that we measured what was happening with it. That was it. And the result was different. Yeah, it's almost like evidence of like intelligent design. It's kind of fascinating. There's something we don't understand, and only when observed does it. It's like, oh, he sees me. Stop doing weird stuff. Go back and doing this other thing. You keep going down that path. There's some experiments that are based off that, where things change actually in the past. So there's time travel involved. Ridiculous.
It's like a teacher that walks into a group that's not paying attention.
Yeah, so that stuff is just fascinating. But so now imagine trying to, if you're writing code for a quantum computer. So what I've started, and this is where it is related to this class, I've started working on an interpreter for quantum gates. And I don't know how far in it's going to end up going. I mean, this is just the start of, I'm using it to like further learn about the stuff, but the idea of programming with probabilities seems interesting, but the amount of data that a qubit can hold is basically infinite. So with a normal bit or normal byte, if you have 8 bits, you can hold 2 to the 8th power worth of unique values, right? All right. Well, so we might say, well, is a qubit's the name of the bit type things in quantum. So we can say, well, how much can that hold? Well, it's technically 3 states. So is it 3 to the whatever? No, it's all values. You can hold all values, but you can only measure one. So then what are you actually doing? You're manipulating the probability of measuring the value you actually want. So I don't know what you do with that. What kinds of problems does that lend itself to? I mean, so one of the famous problems that it's solving almost instantaneously is this idea of the traveling salesman problem, shortest path. And then you start getting into stuff like quantum entanglement, which is creepy in and of itself. You take 2 particles, they're entangled, you can move them an infinite distance apart, and something that happens to one, the inverse happens to the other, regardless of their distance. That's creepy. All sorts of creepy stuff. It's like sci-fi, but it's real. Yeah, so that was my Easter.
Well, it does have quantum in the name.
Well, yeah, but what does that mean? That's just
Science.
super tiny.
No, it just means science and science.
Well, then all values are held in superposition. So superposition says it's one or the other and both. That doesn't make any sense. What are you supposed to do with that? Oh, here was that, where's the thing I was showing you? Yeah, this guy. These are my slides I was putting together for my interpreter. You know, you feed it, this is the 2 different random inverters. You feed it a whole bunch of zeros or ones. You can think of white dots, black dots into the first one, and it's going to be 50 of one, 50 of the other, but then you feed them in again and it gets you back to your original. So something magical happened in the middle here. Oh, unless you observe it. Does change you. Oh. You'll never sleep again. It's a thing. It's a real thing. All right. Nope. We've already wasted enough time. Go ahead.
No, for quantum computing, so like, what if there was like a human being throwing photons? What if you were to throw the left side with your right arm and your and the right side with your left arm? Is it just splits, or is it?
I don't think it would matter. The source of, and we already saw that it doesn't matter which slit you throw it through unless you're measuring it, because it goes through both slits unless you measure it. And you know, some people, actually, a lot of books have been written on this, like the Deepak Chopra books and mysticism and things like that. They write that, oh, the human the brain or consciousness can actually have an impact on the world, you know, using it for like telekinesis ideas and things like that, because they'll take something like this and they'll misinterpret it and say, oh, well, so just by looking at it, you change the outcome. Well, that's a true statement, but the correct phrase is observing or measuring. We can measure it with our eyes, but you don't even need to be in the room. You can just put a camera on there, and the second, if you're having something else measuring which thing is going through, just the act of you're trying to see what's happening changes the output. Doesn't matter if your brain was involved in it in real time. All right, so let's start talking about object-oriented languages. So remind me, what makes, oh, let's see, who's online? We're missing people. Thanksgiving, we always have drop off. So what makes an object-oriented language an object-oriented language? So what's their differentiating factor between a procedural programming language and an object-oriented language? Or maybe you can start off by thinking about it when you learned Java or C++ or even Python, same thing. What's the difference between the way you started off learning it to where you did it right around midterm? What did we add? Go ahead.
With an object-oriented language, you have the ability to create objects.
Okay. Now, typically, when you're first learning programming, even if you're using a language that is capable, it is an object-oriented language capable of creating objects, we typically don't use them out of the gate. We typically are doing procedural type stuff with a language that might be capable of object-orientedness. Okay, but you said that eventually an object-oriented language allows you to create objects. Fine. What's an object? Okay. I'll give you that in a parenthesis. Okay, an object data structure. Okay, so specifically, when we think about objects, what is an object? What are the details of an object? Good. Okay, so a user-defined data structure. Let's not get no parentheses for that one. Keep going. Specifically, what's the DNA of an object? Whether it's user-defined or built into the language. If I were to open up an object and I looked inside, what kinds of things do I see? Go ahead. Okay, anything else? I like the methods part. The data part, what do we call the data associated with an object? Memory address or something. Let's explore the of some sort. That's almost as bad. Let's properties is not horrifically incorrect. Formally, we call them fields, right? We call them fields. And then we also have methods. What else do we have in there? Oh, we have a third kind of thing. Kind of like methods. No, kind of like methods. Go ahead. I'm about to throw up at my mask, which would be funny in and of itself. Or maybe I won't. Superposition. Fields, methods, and what other thing? What other thing make up an object? Constructors. All right. So an object is a collection of fields, methods, and constructors. All right. What's a field? You already said it's the data. It's the variables that an object remembers about itself, right? So variable values that an object knows about itself. All right. What's a method? Potentially, you don't have to operate on the field, but that would make some sense that you're working with the field. So a method, we can think of these guys as the abilities that an object is able to perform, potentially in terms of its fields, and may, now I was just going to throw you a bone and say may take parameters, but it's a normal method. It can take parameters if you want. Okay, so that's what a method is. What's a constructor? Okay. All right, so the tool that initializes a new instance of the object. Now, why might we have more than one constructor? Because I said that it's a collection of fields, methods, and constructors. Are we allowed to have more than one constructor in an object? Sure. Why might we want more than one constructor? Well, so objects are our programmatic way of representing the way we think about things in real life, right? So if we take any random object in real life, is there only one way of constructing that object? Take this coffee mug. Okay, this is the final outcome that we're looking for. All right, maybe we add some variability, because this mug is probably made by some generic company that Acuity paid for and had them put their logo on there, right? Like Acuity probably did not manufacture the mug. All right, so chances are, if we say this mug has a field, has a couple of fields, it probably has a field for the logo of type picture or whatever. It probably has maybe a field for capacity if there's a couple of different size things here. Okay, but that's maybe the things that needs to remember. But in terms of actually manufacturing, in terms of actually constructing this mug, can we, I'm not expecting anybody in here to be a, super expert in how mugs are made, but we can imagine that there is more than one way that you might be able to make something like this, right? There's probably some super expensive machines that take metal and kind of punch it out into the shape or something like that. There might be something else that deals with like melting the metal and kind of pouring it into like a ceramic mold. I see that on How It's Made. That thing, that shows it's fascinating, isn't it? It's a good way to spend like a day on Facebook, or not Facebook, on YouTube. And we imagine there's probably some other ways you can make that mug. So we might have various constructors. We say, I want to build this mug. Here's the blueprints for this. And we can go up different constructors and they say, yeah, I can make that for you. And they might need different components. They might need different inputs, different parameters. But ultimately what they're going to hand you when it's all said and done is a mug. Okay, so that's the idea of why we might need multiple constructors. Okay. So that's what an object is. Are we missing anything that's kind of an important final piece when we deal with objects? The this.self keyword or /self keyword, depending what language you're coming from. In C, or C++, it's this. C#, it's this. In Java, it's this. In Python itself, what's that guy? Okay. So how an object refers to itself from within itself. Why do we need this? Why do we need a special keyword for an object to talk about itself within itself? Go ahead. Well, we can define, if we just want to write Java stuff here. I can say like random R is equal to new random. I defined R. This doesn't have anything to do with this. I just defined it. I have a variable called R that holds my instance of random. No harm, no foul. So if I think about if I'm going to use R to call one of his functions, his methods, maybe he has a method called nextInt, and we can, say, oh, well, nextInt knows how to, maybe the maybe the better thing to do here is say something like person P is equal to new person. Give it a couple of values here. And then maybe we have something like P dot get name. All right. So we definitely have a way of referring to P here. But when we call upon one of P's abilities, one of his methods, and we ask P to get me the name, let me throw a second thing in here. Person P2 is equal to new person Jeff Smith. When I say P2 get name, what's this guy going to boil down to? Good. Give me the right answer. give me a much better answer. What's this line right here going to boil down to? Whatever we implemented get name, yeah. So something in terms of those values, right? All right. P2's get name is going to boil down to what? So even though this was the same ability, this version of get name belonged to this instance of person. So it knew about things related to this particular person. This version of get name belonged to this instance of person, and it knew about things related to this particular person. So even though these functions have identical logic, inside of those functions, they are likely, this is kind of related to what we wrote on this slide, they're likely to perform things in terms of the fields associated with a object. Likely is a relative, but it's not uncommon for us to say that they would operate on those fields. So P's get name knows about these fields, Mike and Lippman. P2's get name knows about Jeff and Smith, knows about those fields. All right. But if I teleport myself inside of get name, if I am inside of the implementation of get name, do I have access to the variable P? Similarly, if I'm inside of the implementation of get name, do I have access to the variable P2? So if I'm inside the implementation of this method right here, do I know about P? I don't have access to that variable. The scope of that variable it's outside of my scope because I'm in some other dimension where this class was instantiated, some place in memory, whatever. And here's a method being written. And so this guy doesn't have that way of talking about his first name and his last name because he doesn't have access to this variable P. So go ahead. Yes, but how do we ensure that we have access to those guys? Because what if I have a let me just give you a strong example for it. Well, a manufactured example. Yes, he would have the scope of those things would be accessible provided he had a tool to reach to them. So maybe giving examples not going to get me any farther down than just words. So the idea is if I'm inside of the implementation of get name and I glance up, maybe I could see the first name and the last name. But really the only things I directly have access to are the variables that are within the scope of get name. Things that either came in as parameters into get name or things that were defined inside of get name. Okay, but because get name happens to be a method that lives inside of a class, in order for this whole idea of building objects to make sense, Those fields way up there should be things that I need to have access to. But as of right now, if we don't have anything special, I don't have any extra tool that kind of came with the idea of objects, I have no way of actually reaching up to those guys. Now, scoping rules do help us in this case, where if I did have, so this is where I think creating a visual. Well, let's say I had a class called person. And I had a string F name, string L name. We had our constructor. And actually, we could just stop right there if we want. Well, I'll just to finish our example. Something like that. So that's our class person in ish pseudocode. Java-ish, C++-ish, whatever. All right. So, and really the best example here is inside of our constructor. Why did I have to say this .f name where I only said F name here? Explain this one line right here. This is a variable, right? Variables, all variables resolve to their most local definition. True statement? That's true in all programming languages. And that's what we've been talking about with our variable environment, right? As we've been resolving variables, we want to make sure that, hey, whatever's the most local definition of this variable, that's the guy I want. I want to make sure I grab the right version of a variable in the event that I have more than one variable with the same name. Okay. So this F name right here, the most local definition of that guy is that definition right there. But since I am inside of, even though this is constructor, he behaves a lot like a method, I'm inside of the person class, this particular instance of a person class. If I want to reference my fields, and I happen to have a situation like this where one of my field names has the same name as one of my parameter names, I need to have the ability to differentiate that. Now, a weaker programmer might say, oh, well, we can fix that. We'll just call that guy FN. And now we can say F name is equal to FN. And that'll work, right? Yeah, that works. All variables resolve to their most local definition. FN is a variable name. It resolves to its most local definition, which is right here. F name is a variable name. Well, it's going to look in the local scope first. Is there an F name defined here? Nope. So it's going to bounce up to the next level. Is there an F name defined here? There is. It's going to find it. So this is perfectly legal. But this would be something I would, this is the lesser programmer, bad programming practice. Why? Well, this constructor here is taking in a value associated with that you want to be associated with the first name. You thought it was plenty good to call first name F name up here. Why wasn't it good enough to call it F name here? Isn't it kind of a cop out for you to purposely name your variable something different just so you don't have to prove that you understand the this keyword? If you're storing the first name, the correct variable or a reasonable variable choice would be F name. Now, if you called it FN up here, then maybe it's reasonable to call it FN here, because then you're kind of saying, oh, I'll recognize a variable built for holding first name by just the variable name FN. That's fine. What I'm saying is that it doesn't make sense for you to name it one thing here and something different here. It's built for holding the first name. Make sense? So if you don't understand the this keyword, you might purposely write code like this. Why? Well, because that's the only way to get it to work for variables resolving to their most local definition. Evidence is here that from in here, we do actually have access to this variable. It is somewhere in my scope lineage. I can eventually bounce up to it. I have access to it because of the way that an object is constructed. But if I want to differentiate myself, this .l name is my way of bypassing local scope and saying, I want to get the variable called L name that directly belongs to this dude. Does that make sense? Okay, so I'm bypassing that rule that says all variables resolve to their most local definition. That is true unless you give it the full path to where that variable lives. Same thing's true like in an operating system. You're sitting out at the terminal and you type something in and press enter. It's going to look in the current directory, for example, as long as the current directory is in your path. All right. But if you type in C:\/ program file, blah, 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 you give it a full path of where to look, you're bypassing that idea of saying, hey, look in the current directory. You're saying, no, go here. Look right here. I've told you exactly where I want you to go find it. Don't check here first. Go there. That makes sense? So this is the idea of giving it the full path of what I want you to set. And I want you to set it to whatever this guy boils down to. This guy boils down to his most local definition, which is the one that was passed in right here. Now, is this legal? Did I say this .l name is equal to this .l name? I'm asking, is it legal? Yeah, sure, it's a waste of time. It's legal. I have access to the L name variable through this keyword. It's a field owned by this object, but now I'm just setting it equal to itself. So I mean, I'm bypassing. I'm just choosing not to use that value passed into the constructor, right? And that value passed into the constructor there, from our example back here, would be either Littman or Smith. Okay. So this would be very weak programming. So we need this idea of an object needs the ability to refer to itself through this keyword from within itself. Whether we're in one of the other methods, whether we're in the constructor, doesn't matter. We need to have some way of talking about ourselves. The same thing's true in real life. If we're instances of objects walking around, so we have person objects, right? Every single one of us in here is an instance of person objects, but we are different instances of person objects, right? What if I said that you had to go through life for the rest of the day and you could not talk about yourself? You couldn't use the word I or me. How often do we say things like, oh, I'm going to go here? Or that's not for me. So what if we made those words outlawed? You weren't allowed to use them for a day. It'd be kind of funny, right? For like a day. Like every single time you have to, like, we'll have to work in teams. So every single time one of you breaks the rule, the other one gets to punch him in the face. And you got to take pictures, like post, we got post every face punch. Somebody comes in on Thursday, just beat up really like 207 times. I just couldn't control myself. The only thing that happened is my jaw swelled shut at the end and I couldn't speak anymore. But wouldn't you agree that that would be a pretty debilitating thing if we didn't have the ability to talk about ourselves, right? Even the word there, the we, in that case, in context, I was talking about myself, right? If we didn't have the ability to talk about ourselves, I'm talking about as a group, all of us having the ability to reference ourselves. It would be extremely debilitating. And we're trying to mimic the way human beings solve problems in real life. If we didn't have this keyword, we're taking away one of the primary things that all of us rely on in order to solve problems in the world. Make some sense? So that is why the self, and language that isn't very popular anymore, called Visual Basic. It was kind of a programming language for non-programmers, and it really created a whole bunch of pseudo programmers with no real programming skills in the world. And it's not that those folks couldn't have had programming skills, it was that they were taught to program using a language that was not a very well-formed language. So they learned a whole bunch of bad habits, and then you had to unteach those habits. But one thing that I did like about Visual Basic is its equivalent of the this or the self keyword was a keyword called me, which that kind of makes some sense, right? Who are you talking about? I'm talking about me. I don't know, kind of makes some more sense than this or self. All right. So would you agree that in all object-oriented languages, some equivalent of this keyword has to exist? We need, otherwise we're very debilitated. Okay. So we go back up here. Collection of fields, methods, constructors. And then we're going to say some way to reference ourselves from within ourselves. We would call that a requirement of an object-oriented language. All right, questions about the high-level aspect of this? Okay, so now from a language design perspective, how do we implement say support into our language? What does that look like? Or how might it look? Anybody want to get the ball rolling? Go ahead. Okay. So we already recently, we did our begin, or whatever we said, whatever we called it, right? What do we call in our language? Our collection of functions, or collection of things that we went through in a row. Huh? Block. Okay, so we created our block structure recently. And I think in our examples, what do? We set a bunch of variables. All right. But in our case here, if we're looking at this this person thing, let's go back here. I'm looking at something like this. When these guys are initially created, so we might say if I'm kind of comparing this to a language like Java, whenever we see these curly braces, that's kind of a block structure. All right. So let's just kind of start with that as a mental base. Right here, this variable f name exists, but it's not bound to a value yet. Right. So now we're kind of going back to an earlier concept of, does something occur free or does something occur bound? Right now, this guy occurs free. He's not bound to a value yet. Okay, but he does occur. He's here. In this block structure, we have created a variable. We just haven't bound it to a value yet. So one thing we have to think about is, what does that mean? Do I throw it into my variable environment? Does it exist? It occurred, right? It's there. So does he belong in my variable environment in whatever the current scope is? Sure, but I have to have some way of flagging it as being uninitialized. I'm gonna have to have some kind of special way of structuring it internally, saying that this guy is uninitialized. Kind of similar to maybe what we did with our scopes when we had our temporary scopes, or we did the inverse where we had our global scope labeled. I think that's what our implementation was, that right? What we did in class, we labeled our global scope, and then any other scope that wasn't the global scope was thought to be a temporary scope. All right, but that concept of saying, I'm going to just mark this guy up a little bit to give it a value that indicates there isn't a value. All right, so what would be some things we can do? If I wanted to put a variable, in this case f name, into my variable environment, but I wanted to somehow flag it that it didn't have a value, what might I do? Give it a value of null? Okay, but isn't null in and of itself a value? Okay, but a lot of our programming languages rely on null as being that default value, right? All right, how do they get away with that? And then before, actually, to ask that question in a better way, let's pause on the null. This is a good answer, but it has consequences. Let's come up with an alternative to null. Maybe put a question mark in there. Go ahead. So like the word no val. Okay, that's fine. Just as good as my question mark. All right. So maybe we create a variable f name in here, and we label it inside of the environment as having a value of no value, or no val, however you want to spell it, right? All right. Now that could work, but what's the negative consequence of that? If I'm going to label all variables that haven't been initialized as having a temporary value of no val, what does that imply about the value no val? Can't use it. It can't exist in my language anywhere else. I can't legitimately create another variable called s and set it equal to the word no val. Words taken. Does that make sense? That word is, so most of our programming languages, well, generally speaking, a programming language would call this a keyword or a reserved word in the language. So reserved words in the language are off limits. So for example, you can't name one of your variables for in Java. For loop is taken, right? You can't name it if. You can't name it while. Now, in general, this is kind of a chicken or the egg type problem, right? We can say, all right, so fine, we have this list of like those common things, and I can't name my variables those things because they've just been marked as off limits, because I mean, the language, we have to give a level of leeway to the language for it to have names for things. Go ahead.
Other languages have like a distinction with it. You can name it like the string.
Well, correct, because that's not the name of a variable. That's the value within it. And the keyword or the reserved word for is distinct from the double quote for double quote value, because that guy is a string. It's a stream of characters that just happens to have those 3 characters in a row, but they're not equivalent to each other because we're not resolving that. It ultimately comes down to a variable environment. We're not trying to resolve the value, we're trying to resolve the variable name. Okay, but if we're using the value of a variable, like I'm kind of saying, I mean, I forced us down this path, right? So if we're using the value of a variable to flag it as not initialized yet, then anything we pick as that placeholder has that's its job, is to be a placeholder, and it's not a value that we can use for other things. Unless it had the same job, the job of being a placeholder, right? Okay, so if we use no val as our placeholder, which makes a lot of sense as to what we're doing, or maybe even the word uninitialized, right? Uninitialized would be probably a perfect variable name or variable value for a variable that hasn't been initialized. But all of a sudden now I cannot store the value uninitialized in any other variable unless it's for the purpose of saying it's actually uninitialized. I no longer have the ability to represent that value in my language. Okay, so what are some ways around it? Just kind of going through the history of computer programming problem solving. Yeah. Yeah, try to come up with a value that nobody's going to want to store that. You know, just bang on the keyboard a whole bunch of times until you just come up with something like, okay, the chance of somebody actually wanting to store that exact value is low. And I'm willing to roll the dice. I'm really willing to take the risk that this is not going to break anything for somebody using my language ever, ever, ever. It's almost like you're hiding the Easter egg in your language, right? So at some point, somebody stumbles upon this variable name, you know, drunken stupor, they hit the keyboard, the same keys get hit in the same order, and they're like, why can't I hold this value? And they go on this, like, you know, this wild goose chase, only to find out that that was just some obscure bad programming placeholder that you put in there, right? And there's interesting, so one of the things, I think I've mentioned it in other classes you've had with me. So, you know, Dr. Locklear and I, we've been here for a while. For a long time, it was just him and I. And we basically agree on almost nothing. Very different personality types of stuff. So when we do agree on something, it's probably gold. So he has this idea of the grand ideas of computer science. That was his research topic and things like that. Well, one thing I like looking at is computer science as a field. Every individual subcomponent of computer science is related to all the other ones. You can see example, we're in a language theory class, and I'm about to make a correlation to database. But you could very easily do that in almost anything. You know, these aren't specialized classes. These are just a look into computer science through a little bit different angle, something like that. So one of the early problems we had with databases was, how do we represent our data? So if you kind of go back to a relatively primitive file format that's still used today, a CSV file. Everybody familiar with the CSV file? What does CSV stand for? Go ahead. Comma separated values. So the presumption would be, based on the name, that it's a bunch of values separated by commas. Now, that would imply that storing a comma as one of your values might be problematic since you're using commas to delineate your values. Does that make sense? So again, it kind of becomes this chicken or the egg problem where, well, I kind of want to be able to store all kinds of values, but I also need some way of separating my value so I can read it in later on. Well, maybe we separate it by spaces. Okay, well, that's even worse, because now I can't have any spaces in my value. Well, that's worse than commas. You know, maybe you just search around the keyboard, you find some symbol like, oh, I've never hit that. You just pick something from the Greek alphabet or something like that, where it's like a really Unicode character that requires some fairly significant searching to find like the right value for it. But it still isn't impossible that you might use it. But we got to give up something, right? If you're going to kind of take the direct, let's just get this done, human problem solving aspect to this, you're kind of hunting for something, like you said, a random stream of symbols that, well, they're probably not going to want to store this. And now you've opened up a door. So we look at our modern languages, and typically an uninitialized value, especially an object type, has in fact, it's probably true to say it's an object type, because if we think about most of our programming languages, the default value for an int, for example, is a 0. And I've mentioned that you should never rely on default values, but they still are a thing, right? Most of our modern programming languages, though, will at the very least give you a warning. Many of them will give you errors if you do try to use, if you say int a, and on the very next line, you try to print out the value of a, it'll scream at you and say, a has not been initialized. So even though it has a value of 0, presumably, the language knows, the compiler knows that you didn't actually give it a value. And that's a problem. You're trying to use a default value, which is always going to be at some level a bad idea. Okay. So it seems like languages do go out of their way over and above the idea of looking at the value that is in there by default and somehow flagging whether or not you did give it a value or not. So that we can think about, well, how did they flag it? But for objects, it's common for us to have null as the default value for an object, or for us to specifically, if we're supposed to return an object type and we don't have anything returned, we could return the value null. That's it's a memory address that isn't a memory address, but it is a memory address. Why is null okay? We said that no value pretty quickly isn't okay. Uninitialized is even more not okay. A comma, definitely not okay. We use those enough, right? We even said that random banging on the keyboard, probably not okay, even though we could probably get away with it. Why is null okay? Go ahead.
I feel like null is already reserved.
Well, was it already reserved, or is it reserved because of this?
Well, I'm more so saying,
Which happened first is the question.
well, I'm more so saying like in the language scheme is reserved as
Why?
Is this a keyword that's supposed to be like?
They just go through and just come up with keywords and throw it in there and say, "Shh, that's reserved." Yeah, nobody can use that. Why? Just because. Yeah. So well, and you could do that, right? As a program writer, you can do whatever you want. So you can just kind of have a list, you know, like I'm going to go to the Q's in the dictionary. We don't want people using any of those. so you're just going to have a list of all the words that start with the word Q from the dictionary. You're just going to set them up as reserved words with no necessary intention of using them in your language. Just, I can't use them and nobody else is going to use them either. We could do that. Logic's kind of out the window at that point. Okay. So, you know, the question is that, so you're right, in all languages, all modern languages, probably the first thing I said, all programming languages, null or something very similar. Some languages it's nil is that, but the equivalent of the idea of null, nothingness, is, or in Python, it's none, right? So the equivalent of nothingness is a reserved word in those languages. So is it that they arbitrarily said that, oh, that we're just going to have that as a reserved word? Is the concept of nothingness something that all languages need to have as just a baseline? Like, I'm going to have situations here where nothingness might be the most appropriate value to store, and I need to have a locked in way of representing nothingness. And this goes back to something that we asked earlier. The word null is a reserved word in most of our languages. But is the string null allowed? Can I have double quote, N-U-L-L double quote? Sure. Just like I can't use the word for, F-O-R, but I can have the string for. Because when you have a string, when you have double quote, some characters, double quote, that resolves to a type. The language is going to look at that and say, ah, this is a string. With a string, I'm going to resolve it to its value. It's a literal value. It's a literal type. As opposed to, if I just had the word FOR sitting there, because that isn't a predefined type, it's going to try to resolve that as if it's a variable name. And the first thing it's going to hit, so now we kind of see that our programming languages, when they go to resolve variables, that's what's probably happening at compile time for compiled languages, but for an interpreted language, it's going to have to do it during runtime. It's going to have like one pass across the list of reserved words and say, before I try to resolve this in my variable environment, I need to make sure it's not one of these guys. Because if it's one of these guys, I want to start screaming now. All right, just in case we wrote a buggy language and somehow allowed them to put a variable name 4 in my variable environment, and it does, or, you know, we did the Easter egg thing and just hid it in there. We put it in our global environment, just, yeah, 4 equals 7. It's a thing. So is it reasonable from a language designer perspective? Is it reasonable for us to say the concept of nothingness is something we should have? Certainly reasonable. And we might not necessarily know how we're going to use it yet, but that idea of being able to represent nothingness is a reasonable idea to have. And it would not be unreasonable for us to sit there, spend 5 minutes, come up with what that word's going to be, null, none, nil, whatever it ends up being, and just settling on it and saying, in our language, that means nothingness. Okay. Having said that, what we did just do, well, let me ask you this. By doing that, did we remove the ability for us to set a variable equal to that value? In our modern day programming languages, can I create a variable? Can I say like, can I do something like, I'll just rotate it here real quick. Random R is equal to null. Can I do that? Sure, that's legal. That's a legal use of the keyword null. Now, if on the very next line I try to say r.nextInt, what's going to happen? What error? If I'm in Java, yeah, null pointer exception, something along there. Why is that? This guy gives me a null pointer exception or similar, depending on what language you're in. Why does that happen? How does that happen? Go ahead. Okay, true. How is that actually, when I say r.nextInt here, what's happening? What's actually occurring? Go ahead. Mm-hmm. I'm going to update this slide title. So we're using a model language here, Java, C#, C++. They all fit this this pseudocode, let's say. You know, null is all caps in C++, but you kind of can roll with it here. All right, this guy right here, is this a relatively common way of a syntactical way of calling upon a method that belongs to an instance of a class? Sure. How might you implement that concept? What's actually happening here? I'm not really asking for a code example. I'm asking for, if you were to articulate what's actually going down here, we're searching for, is there a predefined model for how methods, instance methods in this case, are called? What's actually occurring here? Or if you don't know already, how might you write this? That's something we probably want to be able to do in our language somehow, right? Okay. The dot notation probably isn't going to be overly compatible with our list kind of structure, but we still want to accomplish the equivalent thing. And we're probably going to end up doing it the same way that our modern programming languages do it. So in order to do that, we need to investigate, what does that line do? R.nextInt, if you were to break that down, what's actually occurring? No takers? You knew the exception, you knew the error you were going to get. How'd you know that? You know, how many times I've seen that. So why was that an error? You can even make that jump. Well, obviously you're using null to call something. But is that really what happened? Did we ask nothingness to call something? Hmm. Well, R is a variable which boils down to nothingness. All right, let's use a football analogy. And you can replace it with your, whatever your sport of choice is. It doesn't matter. It's got to be at least a two-person thing, so it doesn't work for golf. Okay, so we'll take, Aaron Rodgers is gonna throw a pass. All right. Well, actually, here we won't even we'll use the real pros, you and me, right? Okay, so you're going out for a pass. So you're going to go out to that corner. You don't have to get up, but okay. And so I got the football, and I turn there, and I throw right there. What's going to happen? Incomplete pass, right? Definitely not going to be a touchdown, regardless of what you were doing over there. All right. Why is that? I took the football and I threw it to nothingness. First of all, it could be an error, right? Intentional grounding, something like that. Let's say it looked like I was trying to throw to him. Right? What were you going to say?
What you were gonna say was
All right. So in our modern languages, we have to consider how are methods actually called. And one approach to this is something called message passing. So we are passing the message to something. Okay. So what are we doing here? We are sending the next int message along with any needed parameters to the place in memory. Well, we don't even need to go into that detail. To R. When we call upon a method, what we're actually doing is we are passing the method call along with the parameters. So this is what I want to do. This is what I believe you're going to need to do it. You're passing it at a destination. Okay. And in this case, R was nothingness. So if I'm waiting for a response here and I just threw my information to nothingness, I'm going to be waiting for a long time. Hence the reason we have runtime exceptions and things like that in our modern languages. Older languages, we replace the word exceptions with just crash. Now we can use try catches to gracefully crash. I'm not sure it's necessarily any better. Maybe half the time it's annoying because we're usually fairly lazy. And what do? We just throw a try catch in there to keep it from screaming at us instead of actually handling the exception. Once you get into doing professional development, you probably want to pay a little bit more attention to exceptions because it might mean that you need to go and do something. You try to retrieve some record from a database and the record's not there. Maybe you want to create the initial idea of the record and then try again. try to update that record again if it wasn't already in existence. All right, so but our modern languages have, they scream at you in some way. They let us know about that incomplete pass. Like don't be expecting a result because you're not going to get one. because you just threw to nothingness. It's a thing. Okay. And the way this is done is through the idea of message passing. A way this can be done is through a means of message passing. Many languages operate this way. In fact, you maybe heard me say this before in some classes, but in a language like Objective-C, we would say like random pointer R is equal to nil. Oh, actually, I'll put it underneath it. Just keep these guys together. And then I would say R next end. So this is the syntax in Objective-C for calling the next int function. So this is a message passing syntax. This is the message. This is who I'm sending it to. Right? But what I'm telling you is what's happening here is identical to what's happening here. It's the syntax is a little bit different. I just think Objective-C makes it a little bit clearer that it's message passing, or at the very least, we're not just getting sucked into our idea of that dot notation, which maybe pulls the kind of eye off the ball type thing of what's actually happening behind the scenes. Go ahead. Null is the antithesis of a memory address. Well, actually, let me think through that a little more. Certainly, null represents the antithesis of a memory address. Having said that, I think your question really is what is null actually? How is null represented in the language? Null would be a literal value, which would live at a memory address, and somewhere would be listed as part of the list of symbols, list of reserved keywords that are off limits in the language for like variable names and stuff like that. But null does exist. The keyword exists, and its meaning is nothingness. Its meaning would be the antithesis of a memory address, but it in and of itself does have a memory address because that literal lives somewhere. So I guess, yes, it's a memory address. And with that in mind, then, since R boils down to null in this case, when we resolve this variable R, and why do we know this is a variable? If I just see this in the wild, how do I know that's a variable? Or maybe the better question is, how do I know it's not a variable? How do I know it's not something other than a variable? Well, what are my literal values in our programming languages? What literal types exist in most modern programming languages? Numbers, chars, which resolve to numbers, strings, and we got a couple different flavors of numbers, right? You got floats, Booleans, which depending on the vintage of your language might just be actual numbers where you can do math with them, which is weird, but you can. Or a little bit more modern language, it kind of locks, it's almost like the null keyword. It locks you into the word true or the word false, which has the meaning of trueness or falseness, but is probably under the hood implemented as a number because computers like numbers. Okay, but bottom line is our programming languages have these innate types. And those types, those literal types, are things that we can check for. So the compiler or the interpreter can say, are you a number? If you're a number, I'm going to treat you like a number. Are you a character? If you are, I'm going to treat you like a character. Are you a string? Are you a Boolean? If you're none of those things, if I've run out of things that I expect to see in the wild, you're either a variable or a problem. One of the two, right? So I got to try you out as a variable. And what do we do with variables? Try to resolve them. Variables ultimately turn into their value, the value that's contained within the variable. So I'll try to resolve my variable. Where do we resolve variables? A variable environment. So we have to go to our variable environment and say, hey, here's a variable name. I need the value for this guy. And that variable environment's going to go and start searching through, and it ultimately is going to give us the value it found. Or in our current case, I think we return a false if we don't find it. I think it's what our current resolve does, is it gives us a false if we don't find the variable. But ultimately, if I search for something in there and I don't get the value, I'm going to get something that indicates that the value didn't exist. But in this case, R does have a value. R is in the variable environment, is it not? It exists. I'm not going to search through this variable environment and not find R. It just so happens R's value is nothingness, which is different than saying R does not exist. Those mean different things. So how do we represent null in our language? Well, we just have to say that that word null means something. In a compiled language, we are afforded the opportunity to have a list of built-in symbols that are reserved in the language, like the word for, like the word while, whatever. But in an interpreted language, during runtime, we don't really have that ability, because all of our things ultimately are strings or variable names, right? We can't, when we take the car of a list and we get the word for off of that, I can't just put FOR there because it'll try to resolve it to a variable. So I have to put the string FOR there. When I have it on the front of a list in no code syntax, maybe my intention is to call a certain function. But nothing keeps me from defining a variable, remembering a variable where A is equal to the string for, presumably. So I've kind of lost that ability to have reserved symbols with that, which does give us a position of weakness. We need to have some way of representing nothingness, or some way of pre-resolving nothingness, saying, are you one of these special cases where I'm not going to go to the, once I get a value out of the environment, so in this case, R is equal to null, once I resolve R and I get its value, I need to have some way of saying, are you actually one of these special kinds of animals? You're not actually a value that I should be able to do anything with, but you're letting me know that, based on our earlier conversation, that you're not initialized, or you're equal to nothingness. You're not compatible with message passing, things like that. Make some sense where we're going with this? All right. So we'll pick up here on, what day is today? Tuesday. We'll pick up here on Thursday and start getting some of this into our interpreter. Questions, comments, concerns, bribes. One quick announcement. I'll put it up on Slack again. I think I put it up at some point a while ago, but I'll remind you, next week, Tuesday, Wednesday, Thursday night, from 5 to 8 p.m. is senior seminar presentations down in the collaboratorium outside of the makerspace. So make every effort to come to as much of that as possible. Support your seniors. Jason's presenting a project there, right? All right. So 5 PM, which day? Thursday at 5. You're the first person on Thursday?
First on Thursday.
Okay. But try to come to as many of those as possible so you get a sense for what projects look like in the 490 class, and you'll know which ones look good and which ones were embarrassing. Okay. All right. I will see everybody on Thursday.